It's my pleasure to introduce and present today Jonah Gannon. He's one of the Guinea pigs of the scheme for the early researcher visitors, the first ones to be here. He's been here for almost 3 weeks now, but there's almost 2 more to go. So after the talk, of course, you're welcome to find him and discuss. Jonah is at Swinburne University of Technology in Melbourne, where he's been doing his postdoc, his first postdoc for almost a year now. So he's going to be telling all about ultra-diffuse galaxies, their relationship with the halo map, and many, many interesting things. So.
Thank you very much for the lovely intro, Emma. I'll get going. So yes, I'm Jonah Gannon. Today I'm going to be talking about ultra-diffuse galaxies and the stellar mass-halo mass relationship. I should say that I did my PhD at Swinburne University and finished up last year. And I'm now working there as a postdoc. I'm also part of this collaboration AGATE, which involves many of the people you see here. And I've joined the Australian Research Council Centre for Excellence Astro3D, which does astronomy studying galaxies. I really do need to point out that this just isn't my work. It's also the work of Jean Brodie, Duncan Forbes, Anna, who of course works here, Aaron, who's over in California, our PhD students, Lydia and Louisa, Warwick Couch, and many, many others. Before I get onto my talk, I just want to introduce to you this collaboration we've launched, AGATE. It's the analysis of galaxies at the extremes. The members are listed down below. And I know what you're all thinking, guys, this is an astronomy acronym. It makes sense. All the letters line up with the ones in the start of the words. What are you doing? And for those people saying that, we want to say that it's a gateway to new discoveries. Or if that didn't quite work for you, we're going to do some rock solid research. For those who don't know, AGATE is a type of rock. Anyway, on to today's talk. So today I'm going to give you an introduction to the stellar mass-halo mass relationship, and we're going to perform a quick thought experiment on it to try and motivate a lot of my talk and why I think my topic is so interesting. We'll then move on to ultra-diffuse galaxies. I'll explain to you what they are and why I study them. And particularly my interest involves something called globular cluster-rich ultra-diffuse galaxies, so I'll introduce those to you. We're then going to have to ask a few key questions that I think my research helps answer. How many globular cluster-rich ultra-diffuse galaxies are there? Can we be certain they really reside in massive dark matter halos? How are they forming? And I'll conclude with a little what's next, what am I currently working on, and of course present my conclusions at the end of the talk, like all talks should. So for those who aren't aware, this is the stellar mass-halo mass relationship. Well, actually, I should be honest, it's not. The halo mass and the stellar to halo mass ratio, it's just a different way of plotting the stellar mass-halo mass relationship where you divide the y-axis by the halo mass. And you're kind of plotting the star formation efficiency of halos as a function of their halo mass. This is a figure from Wexler and Tinker, an awesome review that was actually sent to me by Laura, who works here, to help me understand this better. And you'll see it's been studied by many, 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 many different people since about 2010. There are many ways of deriving the stellar mass-halo mass relationship. You can use abundance matching, parameterized abundance matching. You can do some kind of halo occupation distribution. You can have conditional luminosity functions, various other things, even semi-analytic models like Beirut's universe machine. But no matter which way you do it, you have a very similar shape and profile and get general agreement between lots of different types, where star formation efficiency peaks at a halo mass of about 10 to the 12 and is suppressed in halos that are more massive than this by AGN feedback and less massive than this by supernova feedback, stellar winds, reionization. And so we really actually think that galaxies on the stellar mass-halo mass relationship are telling us something fundamental about the relationship between dark matter and star formation in the universe, and also something quite fundamental about the way feedback regulates galaxy formation. So before we go on, a quick bit of housekeeping. Most of the time throughout the talk, when I show the stellar mass-halo mass relationship, I'm going to be plotting the more simple halo mass versus stellar mass directly. This is one of the relationships that was shown in the previous plot with the indicative scatter that's expected of it. And I'm going to refer to galaxies as being very dark matter rich when they have halo masses that are greater than what you'd expect given the relationship at fixed stellar mass and reside below the relationship in this region. And I'll refer to galaxies as being dark matter poor when they have less halo mass than you'd expect at fixed stellar mass and reside above the relationship in this region. So I also think it's important to know how we build up this relationship if we're going to start talking about it. And so there's this nice quote from the review of Wexler and Tinker. Given the assumption that galaxy properties and halo properties are closely connected, the most important constraint on the galaxy-halo connection is the abundance of galaxies as a function of stellar mass or luminosity. And intuitively, when you get into the kind of nuts and bolts of how you build this up, this becomes very clear to you. What you're doing when you're building a stellar mass-halo mass relationship is you're connecting something that's observable, the luminosity function or the stellar mass function of galaxies, with something that's model dependent, the halo masses in your universe or in your dark matter system, or in many cases, your simulation. And it's quite mathematical and slightly more complex than this, but put in very simple terms, what you do is you get the biggest thing you observe in the universe and you connect it up to the biggest halo in your model. And you do that over and over and over again, each time connecting the biggest thing left to observe with the biggest thing left in your model. And by the end of it, you've populated your stellar mass-halo mass relationship and built up what we see today. And so let's do a thought experiment on this method now. Say you have some kind of fancy new telescope and you're going to survey the entire night sky to unprecedented new depths, or even just a portion of the night sky to unprecedented new depths. And I'm going to put a picture up here of the Dragonfly telephoto array, a telescope that has done this for a large portion of the sky. It doesn't just have to be Dragonfly. This is also going to be done for LSST. Nacho Trujillo at the back does some very deep imaging in which he discovers many, many, many new low surface brightness galaxies. So say that when you do this, you start to find a whole bunch of galaxies that have been previously missed due to their low surface brightness. And I'm going to put this picture up now, which is a picture of the Coma cluster taken by Dragonfly, where they've marked in red a whole bunch of galaxies that were previously missed by studies due to their low surface brightness. Well, what we've done now is we've observed a different galaxy abundance to what's been previously observed. And so what we want to ask ourselves is, how is this changing our understanding of the galaxy-halo connection? So in order to do that, I'm going to return to my previous slide where I built up my stellar mass-halo mass relationship. And this is exactly the same as it was before. Now I've added in an ultra-diffuse galaxy here in blue. And so we're going to go through the exact same method where we start matching up the biggest things we observe with the biggest things in our dark matter model. And it continues normally until we hit this new population of galaxies that were previously unobserved. Once we start to hit ultra-diffuse galaxies, you'll see that it changes because we have to assign this galaxy to a halo that was previously being assigned to a galaxy of slightly less stellar mass. And so this alters your stellar mass-halo mass relationship. I have over-dramatized it in this plot quite significantly. It's almost certainly nowhere near as dramatic an effect as this, but you are actually fundamentally changing the way that we see connecting dark matter to stellar mass in the universe. And you're even starting to change the way we think about star formation feedback, which is supposed to regulate, or which has been previously described as suppressing the star formation in these galaxies simply by discovering new stellar mass in this regime. But this is only really true if there's a lot of them. If I discover one new galaxy, the effect is very minor. But if I discover lots and lots of them, the effect becomes gradually bigger and bigger. So now I need to introduce you to what an ultra-diffuse galaxy is. So this is how I introduce ultra-diffuse galaxies. This image is to scale. This is an ultra-diffuse galaxy over here on the right. I should say that this image is much deeper than the image of the two galaxies on the left. But it has to be so that you can see that the half-light radius of this galaxy is roughly similar to the half-light radius of Andromeda or of the Milky Way disk. But it has a stellar mass much more similar to the dwarf elliptical galaxy. So it's got a dwarf-like stellar mass, but a half-light radius much more like a more massive giant galaxy. And so this actually leads us to a very intuitive way as to how many people have proposed they might form since when they were first discovered, with many saying that they might just be a puffy version of a normal dwarf elliptical galaxy, where you get a normal dwarf galaxy and through some mechanism like supernova feedback or tides, high halo spin, various different ideas, you can puff the galaxy up into the ultra-diffuse galaxy we see today. But yet others have said that because of their large half-light radius, they may actually reside in halos similar to probably not quite the Andromeda galaxy. I think there's quite good evidence now that they're nowhere near that massive, but maybe an order of magnitude less in mass than the Andromeda Milky Way-like galaxies. But that's still quite a lot more massive than a dwarf elliptical. And so we call these galaxies failed because they've failed to form the regular stellar population we'd expect given the massive dark matter halo. That's the intuitive definition, but we do science, so we need a scientific definition. This is a plot from the paper of Van Dokkum et al. 2015, plotting surface brightness versus half-light radius. In this paper, they first proposed the term ultra-diffuse galaxies, and you'll see they've got a large population of SDSS galaxies. They've got this large population of Virgo dwarfs, and in that paper, they discovered all of these galaxies lying in a largely unexplored region of parameter space. You'll see that there are a few Virgo dwarfs that already met this definition, and perhaps one galaxy in SDSS that was already in this region of parameter space. But in order to study this large population of galaxies that have been previously unseen, they came up with this definition of a large half-light radius with sizes above 1.5 kiloparsec squared, or 1.5 kiloparsec, and low surface brightness with central regions fainter than 24 magnitudes per square arc second. And it's really worth pointing out now that this is a completely arbitrary definition. The large half-light radius comes from the pixel scale of the Discovery telescope at the distance of the Coma cluster, and the low surface brightness is a historical term which seems to come from a fight between the astronomer Ken Freeman and the astronomer Mike Disney in the 1970s. And so there's really no physically motivated reason why this definition exists, but we still use it to select out these galaxies in a previously unstudied or largely unstudied region of parameter space. And because the definition is quite arbitrary, it's probably a surprise to nobody that UDGs are quite a mixed bunch. So these are two ultra-diffuse galaxies that I've chosen to be at either ends of the spectrum. These are both Hubble Space Telescope's images of them. This galaxy here, AGC phone number, is a blue star-forming field ultra-diffuse galaxy. It's got lots of H1 gas. It's got a stellar mass of about 10 to the 7, and it's got two orbital clusters, these little point-like sources there and there. You can see it's very irregular in morphology, it's got star formation, and that's contrasted quite a lot by this galaxy over here on the right, NGC 5846-1. It's got a stellar mass that's quite similar. It's an order of magnitude more, but there are plenty of galaxies that look like this AGC with a stellar mass of 10 to the 8. And in the Hubble Space Telescope imaging, you can see there's quite a stark difference between this one having lots and lots and lots of little compact sources associated with it, and this one having two. And so this actually has 54 globular clusters associated with it. Those of you who don't know, a globular cluster are these little things. They're a ball of 100,000 to a few 100,000 stars. They're thought to be a byproduct of all star formation, of all galaxy formation for galaxies of sufficient mass. And they're very, very interesting to us astronomers because there's an established relationship that globular clusters indicate halo mass. So this is a plot from Burkett and Forbes 2020. It's plotting total halo mass on the x-axis versus globular cluster number on the y-axis for things ranging from dwarf galaxies all the way up to the most massive clusters. And you'll see that there's this, observations are in red and a best fitting line is in black. And you'll see that there's this very tight relationship where if you go to a system and simply count the number of globular clusters in that system, you're getting a very good estimate of the total halo mass of that system. So the total halo mass of the galaxy is simply 5 by 10 to the 9 times the number of globular clusters in that system. I should say that we've already got confirmation of this relationship for only one ultra-diffuse galaxy. It's the ultra-diffuse galaxy Dragonfly 44. It's got a resolved velocity profile, which gives a halo mass of about 10 to the 11.3. And they've got two separate globular cluster counts that are in slight disagreement. But if you take the top many globular clusters or the few globular clusters, you still find the galaxy lies on kind of within the scatter of this globular cluster number halo mass relationship. So we do have some early evidence that we can apply this to ultra-diffuse galaxies. So let's return to our plot. this is our stellar mass halo mass relationship. And in my little thought experiment, what I told you was that if we go out and find many, many more ultra-diffuse galaxies or many, many more of any type of galaxy, what we may actually expect is that in changing the abundance of our galaxies, we are starting to see that star formation might be a little bit more efficient in these regimes than what we were expecting. Again, probably not quite as dramatic as this, but we might alter the relationship up. But with these globular cluster rich ultra-diffuse galaxies, when you get an estimate for their total halo mass coming from their globular clusters, you find that galaxies such as 5846 UDG1 reside here. Rather than being dark matter poor, they're actually very, very dark matter rich. And it's very, very difficult theoretically to explain why this may form. There's not a good reason, as far as I've been able to come up with, or many others have been able to come up with, as to how you get a galaxy that's so greatly suppressed in its star formation. And I should say that this is why we've called ourselves the Agate collaboration. These are the galaxies at the extremes and many others that we wish to study. So again, our thought experiment was, what if we observe a different galaxy abundance to what has been previously observed? And we thought that maybe we might see that star formation feedback is a bit less efficient than what we were previously saying. But our new idea is that we've got these galaxies that lie in this largely unexplainable region of parameter space. So what if our current galaxy formation model is simply missing something to not be creating these massive failed dark matter halos? So in order to try and convince you that we can do this, I need to convince you of a few things. First of all, I need to tell you how many globular cluster rich ultra-diffuse galaxies are there. Because this is really only a problem for galaxy formation if there's more than one of them. If there's only one of them, then you can just explain it by the 3 or 4 sigma scatter in the relationship. Something has to be there. If you look at 10,000 galaxies, eventually you'll find something that lies this far off the relationship. They'll still be very interesting to study, to try and work out why they came there, but it's not really telling you anything new about physics. I then also need to give you a bit more evidence that they reside in these massive dark matter halos. We've got confirmation for one galaxy that this is likely the case, but one galaxy does not a relationship make. And if I can convince you of the first two, I think we can start to have a look at some interesting questions as to how they may actually be forming at the end of the talk. So let's jump right in. How many globular cluster rich ultra-diffuse galaxies are there? So in order to answer this question, I'm going to start with the much more general question of just simply how many ultra-diffuse galaxies are there? So this is a plot that gets made whenever a new type of galaxy or class of galaxy is discovered. The halo mass of the environment that you find them in versus the number of them you find them in. The number of ultra-diffuse galaxies, or the number of galaxies you find in that environment. And the reason you make this plot is because if environmental processes play a role in forming the galaxies, then you expect to preferentially find more of them in cluster environments than you do in groups. And so if the slope of this line is much greater than 1, you can tell that tides are playing a role in the formation of the galaxies. So in this plot, you see the slope's very close to 1, and so it's not clear to us that the environment plays a role in the creation of these galaxies in a large manner. There's certainly some that are known to be tidally formed. So from this plot, let's take an example. Let's take the Hubble frontier field at a redshift of 0.308. The reason I chose this is simply because JWST is looking at it. There are tens of thousands of galaxies thought to be associated with the cluster. A reasonable guess is in the 30 to 40,000 range. And based on the work of Janssens et al. 2017, we know that 5% of all galaxies in the cluster are ultra-diffuse. So 30,000 galaxies, 1,400 of them are UDGs, you can get an estimate. At the other end of the spectrum, you might be interested in galaxy groups down in the Milky Way type regime. You can have a look at Ariana DeCintio's work, which we talked about last Friday, where she says that 20% of group galaxies may be ultra-diffuse from her simulations. Observationally, I think the constraint comes out at more like 7 to 10%, but across the entire range of the universe, no matter which environment you're in, it seems like between 5 and 10% of all the galaxies you find in that environment are ultra-diffuse galaxies that have been previously missed by studies. This isn't answering the more general question, though, or sorry, the more specific question as to how many are globular cluster rich. And because they're globular cluster rich, we might expect them to lie off the stellar mass halo mass relationship. So in order to answer this question, I'm going to turn to my PhD supervisor, Duncan Forbes' 2020 paper, where he got globular cluster counts for a whole range of ultra-diffuse galaxies in the Coma cluster coming from 3 separate studies, and plotted them. They converted the globular cluster counts to halo masses and plotted them on the stellar mass halo mass relationship. So here, stellar mass in the y-axis, halo mass in the x-axis. The line is a established stellar mass halo mass relationship. Dwarf ellipticals are plotted in green, dwarf irregulars are plotted in blue, and this new population of ultra-diffuse galaxies are plotted in red. And you can see that almost half of the galaxies in their study in this region lie below the stellar mass halo mass relationship in this very dark matter dominated, dark matter rich regime, with stellar mass or with halo masses much greater than you'd expect given their stellar mass. And so if, a very large fraction, 5 to 10% of all galaxies are ultra diffuse, and if some large fraction of them may be off the stellar mass halo mass relationship, we can't really start to explain this just as statistical outliers. We need something better. But before we do that, I then need to convince you, can we be certain that they reside in these massive dark matter halos? So in order to do this, I created a sample of ultra-diffuse galaxies in the Perseus cluster. It's very, very time intensive to observe these galaxies. It takes roughly half a night of 10-meter telescope time to get the kind of properties we would like. And so we can't observe them in large quantities. So in this study, I chose my 5 UDGs and attempted to control them for size, for surface brightness, and for cluster-centric distance. And the reason you control for these 3 things is all of them have been shown for normal galaxies correlate with globular cluster richness. And so you have these 3 galaxies here that we say are all very globular cluster poor, and we have these 2 galaxies that are globular cluster rich. And I think you can almost see this by eye, where there's many more compact sources associated with these 2 galaxies. My pointer's died. Associated with these 2 galaxies than are associated with the globular cluster poor galaxies. And this is just a plot of them directed from the sky to prove to you that they are roughly at the same distance. Once you do this, you go away and you spend half a night of 10-meter telescope time on each of them. You collapse down all of the data in your IFU. So this is Keck spectra coming from the Keck cluster probe imager. You collapse it down across all the spatial directions to get a single spectrum in 4 or 5 hours of time. And from these spectra, you can measure redshift. So the spectra are in black, and the best fitting PPXF redshift is in red. Once you've got a redshift, you can confirm that they are indeed part of the cluster. In doing that, you get some confirmation of their status because you've got an estimate of the distance, and so confirm their large physical sizes. But much, much more interesting to me is you can measure the width of these lines. And for those of you who don't know, the width of these lines for pressure-supported systems is a velocity dispersion, and the dynamical mass of a galaxy goes as the velocity dispersion squared times the half-light radius. So if we're going to start to see if these galaxies should follow the GC number halo mass relationship, then there's probably this really first order expectation that as something increases in globular cluster number, it increases in halo mass. What we want to also say is that as something increases in globular cluster number, it should probably also increase in dynamical mass in the central regions. I don't think that's a crazy assumption to make. And so if the dynamical mass goes as the velocity dispersion squared times the half-light radius, we may also expect to see trends with globular cluster number and velocity dispersion and globular cluster number and half-light radius. And so if we step through this plot panel by panel, we're plotting a globular cluster number versus half-light radius. And I should also say that we've sectioned our galaxies into 2 populations, those that are very globular cluster poor and those that are very globular cluster rich. And the reason we divide this is just because things that are globular cluster rich are expected to have halo masses above about 10 to the 11. And in doing this separation, we're saying that these galaxies probably lie off the stellar mass halo mass relationship, whereas these galaxies may follow the stellar mass halo mass relationship. So anyway, back to looking at trends. When you have a look at the trends between globular cluster number and half-light radius, I really think that there's no clear trend where if you increase globular cluster number, you're also increasing the half-light radius. But this is actually simply because of my data selection, where I've selected these galaxies to all have the same half-light radius. It becomes much more clear when we move to velocity dispersion, though, that as you increase the number of globular clusters in our observed camp of ultra-diffuse galaxies, you also seem to end up increasing the velocity dispersion. You end up with dynamically hotter systems. And the net effect of doing this means that there's this trend here, whereas you're increasing the dynamic, or as you increase the globular cluster number of a galaxy, you're also increasing the dynamical mass you measure for that galaxy centrally. And that matches almost exactly with what we expect, given a kind of first order assumption that as you increase the globular cluster number, you're also increasing the mass of the dark matter halo for that galaxy. Yet the second bit of evidence why we think these galaxies should be lying off the stellar mass halo mass relationship, I need to return to this plot of Wexler and Tinker, and all I need to point out to you is that it's got this very characteristic U shape. The peak, and it's got a U. The other thing I need to point out to you is that all the axes of this plot are completely unobservable to observers. As observers, we don't observe halo masses, and while we observe luminosities, luminosities aren't stellar masses. You can convert them reasonably accurately, we think, but we still don't actually observe stellar masses. And so when we try and create this plot as observers, we do it like this. We plot the dynamical mass within the half-light radius, which we use as a proxy for the halo mass of the galaxy, and we plot the mass-to-light ratio, or the dynamical mass divided by the luminosity within the half-light radius, which is another way of, which is the opposite of the stellar to halo mass ratio. So here we're kind of plotting our proxy for halo mass divided by our proxy for stellar mass. And you can see that for normal galaxies, there's this characteristic U shape that's been inverted by the observer's choice to plot the y-axis in the invert coordinate. And so for normal galaxies, this has a characteristic U-shaped relationship. When we plot a whole bunch of ultra-diffuse galaxies where we've measured their dynamical masses, they lie off the relationship. There's this very large trend. And this is, again, kind of the region you'd expect them to reside in under this first order assumption that these galaxies, particularly up here, have halo masses above what you'd expect given their stellar mass and lie off the stellar mass halo mass relationship. So hopefully I've given you some evidence now that there's a large population of ultra-diffuse galaxies and that many might be globular cluster rich. And hopefully I've also given you some evidence that we have some confidence that they may lie off the stellar mass halo mass relationship in these massive dark matter halos, at least a fraction of them. And so the question is now, how are they forming? So one of the first things we can do when we are investigating how these galaxies are forming is, if we're confident that the globular cluster number gets an estimate of the total halo mass, and we've also got a measure of the dynamical mass within the central regions, we can compare the two. So this is plotting the radius from the galaxy center, that's the mass enclosed within that radius. We've plotted dynamical mass measurements for globular cluster rich galaxies in red, globular cluster poor galaxies in blue. And this division has been made again, so that globular cluster poor galaxies have a halo mass of about 10 to the 10, and globular cluster rich galaxies have a halo mass of about 10 to the 11. And now the only really free parameter in this plot is what halo profile I assume to compare the galaxies, because you'll have to extrapolate my total halo mass measurement from large radii into the central regions to compare it to the dynamical masses. So in doing this, I can assume a cuspy NSW-like halo. But when I do that, the halo masses of 10 to the 11, the red dashed line, we expect to agree with the red points. And there doesn't seem to be that good agreement there. Where there is much better agreement is when we assume a chord halo profile, which is around the Cyntia's 2014 profile. You'll see that the red points do indeed agree much better with a 10 to the 11 mass halo, which I say provides quite good evidence that many of these galaxies we expect to have a dark matter core. Or put another way, if you assume that the total halo mass coming from the globular clusters is correct, chord halo profiles provide much better fits for our currently measured dynamical masses. Oh, like that one. The next thing we want to do is start to compare the simulations But before we compare the simulations, I want you to try and get an intuitive idea as to what we expect to have happen. So throughout this talk, I've shown you kind of 3 types of ultra-diffuse galaxies. Those that are very blue and star-forming in the field, those that are very globular cluster rich and slightly denser environments, and those that are very globular cluster poor and denser environments. And so under these assumptions, what we probably expect is that if you get something that's very gas-rich field star-forming, throw it into a cluster, you're going to end up with something like what we're seeing in the clusters. You're going to preserve the small globular cluster system. It's going to fade, become red, quiescent, quench in time. And so these objects probably lie in very, very similar dark matter halos. There's also these 2 simulations that have simulated UDG mass profiles, Fire and Nihao. They both do it with very, very high resolution, including a lot of physics. And because of that, they don't have the most massive cluster environments. And so they're primarily simulating field gas-rich ultra-diffuse galaxies like this one up here. So we probably expect all of these to agree with each other. They should have masses very, very similar. On the other hand, this isn't the case for the globular cluster rich things. If these reside in much more massive dark matter halos, they should have much more mass. So let's put up the plot. So here I'm plotting radius from galaxy center. This is the mass enclosed within that radius. I have H1 rotation curves for these gas-rich UDGs in green. I have dynamical masses from velocity dispersion for the DC poor, the cluster poor things in blue. I have dynamical masses from velocity dispersion for the cluster rich things in red. And I have this spread of mass profiles coming from simulations of Nihao, Fire in orange and purple. So how did our intuitive ideas hold up? Well, firstly, I think that the gas-rich and the globular cluster poor galaxies have very, very similar mass, which is exactly what we'd expect if these galaxies are simply an evolved population of the field of diffuse galaxies. You throw them into the cluster, you quench them, you get what we're seeing here. But 2 populations don't seem to agree anywhere near as well with the simulated UDGs. So when simulations are simulating ultra-diffuse galaxies that are gas-rich and in the field, they seem to be creating too much dynamical mass in the center of these galaxies. The other thing that's very interesting is that the globular cluster-rich ultra-diffuse galaxies have halo mass or have dynamical masses centrally seem to be slightly more on average than the gas-rich and globular cluster-poor ultra-diffuse galaxies, which again is what we'd expect if these really do reside in more massive halos. That's comparing the total, the dynamical masses though. We can also compare the total halo masses I'm doing in this plot. So this is from my 2023 paper. It's plotting halo mass on the x-axis versus stellar mass on the y-axis. You have a couple of established stellar mass halo mass relationships with indicative scatter in brown and gray. I've got the stellar mass halo mass values for the simulations of Nihao and Fire. The observed gas-rich field galaxies, where you get an estimate of their total halo mass coming from fitting their H1 rotation curve, plotted in green. The observed globular cluster-rich field UDGs, you get an estimate for their total halo mass coming from their globular cluster count in red. And here I don't plot the observed globular cluster poor galaxies simply because there's not enough globular clusters around them to get a statistically significant estimate of their halo mass. It'll vary quite wildly with an extra 1 or 2 globular clusters. And so I think that you can see here that for the most part, simulations are creating UDGs that follow established stellar mass halo mass relationships. They seem to be creating UDGs that are simply normal-ish dwarf galaxies that lie on the relationship. But observationally, we're seeing 2 very different populations of galaxies. We're seeing these gas-rich field objects that may have quite a bit more stellar mass than you'd expect, given their halo mass. And so they're very, very dark matter poor. But we're also seeing this population of very globular cluster-rich ultra-diffuse galaxies that have halo masses more than what you'd expect, given the stellar mass halo mass relationship. And kind of neither of these seem to agree overly well with the simulations, suggesting that they're still yet to be simulated by at least these two simulations. So if simulations aren't reproducing them, and it's certainly the case, I'm not aware of any simulation that has reproduced, particularly these massive pale dark matter halos, then we want to start to come up with a little toy model as to how they might form. And so my toy model that I have has two key ingredients. You want fast star formation at early times, because this is known to create more stars in globular clusters. It also concentrates the supernova feedback, which may lead to large mass outflows and create a dark matter core. This dark matter core will increase the galaxy's susceptibility to tidal forces, and these two in conjunction will create a large size. But you also need to stop this fast star formation, because if you continue to form stars very quickly throughout the age of the universe, you're not going to end up with an ultra-diffuse galaxy. You're just going to end up with a normal high surface brightness galaxy. And once you stop forming these stars to quench the galaxy, you can passively evolve it, and you end up with low surface brightness ultra-diffuse galaxy. And I actually think we've already got a little bit of evidence that many UDGs may follow this. So this is a plot from a PhD student I work with, Louisa Buzzo's 2022 paper. We've also got similar results coming out from spectroscopy from Anna, who's been submitted, following metallicity versus stellar mass. You have the established mass metallicity relationships plotted as the various colors. And what I mostly want you to focus on is this population of very globular cluster rich, plotted in red, ultra-diffuse galaxies down here, that don't seem to be following the mass metallicity relationships known for normal dwarf galaxies, but instead lie on this green dotted line. And this green dotted line is the mass metallicity relationship for galaxies at a redshift of 2.2. And so if you get these galaxies, you form them very, very quickly early on, you quench them very, very quickly early on, and then you just let them passively evolve the rest of the universe, you probably do expect them to follow the mass metallicity relationship at the time in which they form. The other bit of evidence that as to why we think that this might be true, that these galaxies are forming quickly early, actually comes from their positioning in stellar mass halo mass space. And to do that, I need to admit that I've been misleading you a little bit when talking about the relationship. When I've been talking about the stellar mass halo mass relationship, I've been talking about it pretty much exclusively at redshift 0. But what I haven't mentioned is that it actually evolves quite a lot with time. So this is a plot from Wexler and Tinker 2018 / Ruzzi 2018. It's from the review, plotting halo mass versus the stellar to halo mass ratio. And you'll see that at very early times, start up at a redshift 10, the first dark matter halos start collapsing. And as the universe evolves, the redshifts of 9, 8, 7, 6, the dark matter halos grow much quicker than the stellar mass of the galaxies. And so you get to a time at about a redshift of 3, where galaxies are the most dark matter dominated they're going to be. Then at this redshift 432 period, this is the famous peak and Stott cosmic star formation history, the Mandow and Dickinson plot. From here on, galaxies become much more efficient at building up their stellar mass than at growing their dark matter halo. And in doing this, the stellar mass halo mass relationship then evolves back to what we see today at a redshift of 0, is plotted with the black line. That's the black line. And so when I say that these ultra-diffuse galaxies aren't following the stellar mass halo mass relationship, I'm saying they aren't following it at a redshift of 0. But they actually come much closer to following it at a redshift of about 2, 3, 4. At this redshift where we think they may be quenching, they seem to be much closer to following the stellar mass halo mass relationship, and they just don't have the ongoing star formation that would take them up back onto the relationship. They don't experience the evolution that many other galaxies seem to do throughout the rest of the age of the universe. And so if we find a lot of these galaxies in clusters, and I'm telling you that we expect that they quench very early, a reasonable expectation may be that this quenching is environmentally driven. And if that's the case, then we expect the things that lie off the stellar mass halo mass relationship, globular cluster rich ultra-diffuse galaxies, should be falling into the cluster at earlier times than the globular cluster poor ultra-diffuse galaxies, because the globular cluster 4 ultra-diffuse galaxies can conceivably be just a field population that keeps getting accreted throughout time. So here I'm plotting a plot of the normalized radius from the cluster center, just the normalized velocity from the cluster mean. It's the phase space plot of the cluster. And the point here is that galaxies that infall when the cluster is younger, infall when the cluster is less massive. And because they do it when the cluster is less massive, they get less energy from falling into the gravitational potential well, since they have smaller velocities, and they are also more bound to the center of the cluster. And so this phase space plot has been color-coded by the regions of Ari et al. Simulations in 2017, based on the expected infall time of the majority of galaxies in these regions. And so if our expectation is that globular cluster rich things infall earlier than globular cluster poor things, we expect them to mostly be found in this region. Well, globular cluster rich things should be in here, whereas globular cluster poor things should be in the outer region. I can throw down a whole bunch of ultra-diffuse galaxies on this plot, and then I can color code it by the globular cluster richness. And so our expectation leading into my color coding was that all the red things should be here and all the blue things should be out here. All my globular cluster rich things should be very bound to the center of the cluster. All my globular cluster poor things probably only be being accreted now. But that's not the case. And so I actually think that we need to start to explore some other quenching model as to how these galaxies quench that isn't environmentally driven. I should say we also have evidence for some of these globular cluster rich galaxies being in the field or even in group environments. And so it's really very unclear as to how you can environmentally quench something in the field or in a group, or less so the group, but certainly the field. So it's at this point, I want to raise your attention to this review of dwarf galaxy formation by Laura Sales that's published last year. Baryonic solutions and challenges for cosmological models of dwarf galaxies. It's essentially looking at what are the biggest problems currently in hydrodynamical simulations of galaxy formation, and how much of attention there are, especially for dwarf galaxies. And so they've had this nice table where they summarize how difficult things are to reproduce in simulations. And I actually really think that by studying ultra-diffuse galaxies, I can inform some of these biggest problems today in current simulations. So the great diversity in dynamical masses I've been talking about is a subset of the diversity of rotation curves problem. The great diversity of dwarf galaxy sizing problem, if ultra-diffuse galaxies are a largely new, unexplored population of large dwarf galaxies, it poses a further problem. If we aren't quite understanding how they're quenching, then there's this quiescent fraction problem. A large portion of my talk has been about the stellar mass-halo mass relationship, so I hope that I convinced you that in studying them, we can help to inform this. And also, I've presented some evidence as to why we think ultra-diffuse galaxies may have a dark matter core. So I think by studying this interesting population of galaxies, we really can inform some of the biggest problems facing simulations currently. So that's most of what I wanted to talk about in my own work. So what's next? Well, for the field, I think what we really want to do is start to measure some much more accurate mass profiles with globular cluster rich UDGs to really accurately constrain their positioning on the stellar mass-halo mass relationship. This will give much better independent results to confirm that they follow this relationship, the globular cluster number halo mass relationship. I also think we need to start looking more into the globular cluster poor ultra-diffuse galaxies, because up until now, we've been very interested in this kind of weird class of the globular cluster rich things, because our expectation has been that the globular cluster poor things are just the large size end of the dwarf galaxy size distribution. But that's only true, or that's an assumption. We need to actually study this and confirm it. And finally, I also think we need to start to look a bit beyond clusters to see if we can start to establish these evolutionary links between field and group objects and their cluster samples. Because a lot of our observations at the moment are very biased to Virgo, Coma, and Perseus clusters. So I'm very excited because the Keck telescope is commissioning this new cosmic reionization mapper. It's the red arm of the IFU I love to use. But you can also do this science a lot with MUSE, because it's very, very good for getting a large field of view and studying the globular cluster populations. But I also really want to point out that some of this science is very, very doable, and very, very, like Megara, this is an excellent science case for Megara, particularly measuring mass profiles for some of the globular cluster rich things. Because you have these positionable fibers, you can get lots and lots of globular clusters from different galaxies, all in the fibers at the same time, and measure masses out to large radii beyond the core. And so when you do this, you can use a single mass measurement to provide a much better constraint as to the total dark matter and total halo mass of the galaxy than we are currently able to do with these central dynamical masses. I also want to say that we really need to move beyond UDGs because the definition of an ultra-diffuse galaxy is very interesting, led us to a lot of interesting discoveries, but it's not clear that the thing that causes the galaxies to be very globular cluster rich and lie off the stellar mass halo mass relationship is also the thing causing them to be very low surface brightness. And so this is a plot that I made from a telescope proposal, plotting V-band magnitude versus the cluster number. And here I'm using this as the proxy for stellar mass, and this for the proxy for halo mass. And I think we should start to select out galaxies that have very high globular cluster counts for their stellar mass, regardless of their surface brightness, to see if this is simply a trend with ultra-diffuse galaxies or if there's something else going on here. Okay. These are my conclusions. So I think ultra-diffuse galaxies are a non-negligible population of galaxies across all environments. We have some reasonable evidence that at least some, or even a significant fraction of them, reside in very massive dark matter halos. At the moment, simulations are struggling to reproduce them. I think that globular cluster rich ultra-diffuse galaxies are probably not an evolved state of just H1 rich field ultra-diffuse galaxies, but perhaps the poor samples we see in clusters are. I think we have some reasonable evidence that at least some fraction of the globular cluster rich things are these passive relics of Z=2 galaxy formation. For some reason that's capitalized. And just to finish on a pun, the future of this faint science is bright with large IFUs. So thank you. Do you have any questions?
Thank you very much, Jonah. Is there any questions? Jonah?
Thank you very much for the interesting talk. Just a curiosity. If I study the stellar mass versus the aeromass relation, you consider the baryonic mass versus aeromass, does the situation improve with what?
It's difficult because there's a wide trend. And so for galaxies such as our globular cluster rich things, a lot of the time they're in clusters. They've got almost no gas or no H1 gas. There's no X-ray detections or UV detections suggesting they don't have any hot halo gas either. And so we think that the vast majority of the mass seems to be in the stellar mass of the galaxy. But galaxies such as these H1 rich field dwarfs, it actually goes the other way, where they seem to have a very, very large amount of H1 gas associated with them. And actually, a lot of the masses you measure seem to be almost consistent with the stars plus gas alone. And it's still difficult to do the modeling in a way that's believable, but within largish errors, it seems to be consistent with having very little dark matter for a lot of them. And so, yes, you've got some consistent with being baryons alone and some that are consistent with being, 99.99% not baryons. So.
Okay. Could you show us the number of globular clusters versus halo mass relation that you showed at the beginning? Yeah. So the halo masses that you have been talking about go from 10 to the 10 to 10 to the 11 solar masses. So all the UDGs are around 10 to the 10 to the 11. And in this has a very, very large scatter relation. So the question is, to what extent part of your results might be due to the fact that you are not really measuring halo masses, but number of globular clusters. So Is this scatter somehow influencing your conclusions?
Very good question. It's difficult to say with the statistics we've got now. I would say that particularly when talking about things, I think it was perfect before. I've lost my plot, but when I showed the plot of the coma cluster where they've got stellar mass versus halo mass, where I showed stellar mass versus halo mass, and there was this large population of nearly half the ultra-diffuse galaxies off the side. Sorry, I just remembered where it is. I think that you can probably use the scatter to explain one or two of them, but if I was to have half of the galaxies over here off the side,
This is exactly what I was trying to point out. So everything's between 10 to the 10, 10 to the 11. So have a look at your relation. And I mean, it's very poorly defined, actually. So within this range, the number of global clusters hardly traces the dark matter here. That's my impression.
I think the number of
So I think that, well, this might
statistically
be
traces is
just-
probably the more accurate way of saying it. But I guess what I'm saying is that you can explain one galaxy as having a globular cluster number that, you know, there's a large scatter in the relationship, and so it could scatter off. But when you have a large population of galaxies, in order to put these on the relationship, I would need some kind of systematic offset in the globular cluster halo mass relationship for the galaxies. I think, yeah, we will have to discuss this later. Sorry.
So among the lower cusp rates, what is the one that falls?
It's quite easily the globular cluster rich. Globular cluster rich. Part of the problem with a lot of these galaxies is that I'm very greedy if you want to simulate them. And so you need to have star formation feedback because that's going to create the dark matter cores I observe. You need to have the full range of field to massive, you know, coma clusters, and you also need to have sufficient resolution to actually resolve these galaxies without getting into your softening limits. And to date, there's no real simulation that can do that. There's just not the computing power. And so most simulations focus on either involving all the galaxy formation physics in a field environment, anyhow. And when they do that, they're recreating the dynamical masses of the globular cluster rich things, but the halo masses of the globular cluster poor things. In the other environments, when they simulate the entire, like there are simulations that simulate coma-like clusters that don't include all the physics, and they don't tend to have the resolution. And the problem they run into is that everything's an ultra-diffuse galaxy. And so they say, look, we can recreate ultra-diffuse galaxies. You know, these are our results. But 80% of all galaxies in this stellar mass range are ultra-diffuse in their simulation. And so it's not clear to us how they, because there's not this differential study, we can't really say certainly what's causing them to form. They're really just telling us how dwarf galaxies.
This global cluster range would be like a relation or between the global cluster, the number of global clusters and the mass of the galaxy.
So at the moment, we think that they just follow the relationship for normal galaxies, that there's no systematic offset.
There's no secret.
But it's going to take a lot of confirming. It's extraordinarily difficult to get independent halo mass measurements for these galaxies. The one that has it's required almost 3 nights of 10-meter telescope time. So
thank you. Very good talk. I just want to ask a very sticky question on observational aspect. How do you distinguish those globular clusters in ultra-diffuse galaxies from the stars?
It's definitely not a stupid question. So there's a few ways that we do it.
I mean, the stars in our galaxy.
Yeah, stars in our galaxy. So you can see, like in this plot, there are some stars in our galaxy in it. I'm pretty sure that's definitely a star in our galaxy. And a couple of these down here are known to be stars in our galaxies. And so globular clusters are thought to form very early on and have very known metallicities and ages, which means we have a good idea as to what their colors should be. There are two other bits of information that really help. The first one is you can plot the density profile of compact sources. Because we know that at this distance, these objects should be mostly unresolved, you can do a selection that makes sure they're compact, which will also select stars. But if you plot a density profile of compact sources going away from the center of a galaxy, then you'll see it fall off a bit like a Gaussian or a Cirsic or something. And when it hits the background, you'll get a very good estimate to how many compact sources are associated with the galaxy in a statistical way. And once you combine that with the color information, you can estimate it.
Right. This works fine with the globular, the rich galaxy, but for the globular, for example, in the lab, there are only two of them. The only information we can use is the color, right?
Basically just the color.
And you have to use multiple band observation.
Multiple.
Thank you.
There is also a comment from Ariana Disindio. Great talk. Thank you. As we already discussed, it would be great to see how much the stellar mass and the halo mass relation change by including 20 and 30% of extra galaxies.
Thank you.
Okay, if not, here, and thank you again.
Thank you.